right, the Compton effect. So the reason we study the Compton effect in Physics 30 is that it's another experiment that confirmed that EMR, or light, behaves as a particle. So in the Compton effect, we took a beam of high energy X-rays and we directed them at a thin metal foil. So this purple squiggly thing is an X-ray photon. And to begin with, it has a high energy. And we're sending these X-rays at a piece of metal foil. So you can imagine like aluminum foil or something like that, only it doesn't need to be made out of aluminum. It could be made out of any metal. And within that foil, we have atoms, and those atoms contain electrons. So here we're just looking at one of the electrons in the foil, and that electron is currently at rest. And what Compton found is that when the photon hits the electron, it actually knocks the electron out of the metal foil. And that's now what we call the scattered electron. And then the X-ray passes through the foil, and this is what we call the scattered X-ray photon. And so what's actually going on here is that we have a collision where the incident X-ray photon is transferring some of its energy to the scattered electron. So that means that this photon over here has a lower energy than before. Okay, when high energy X-rays hit the metal foil, Compton observed ejected or scattered electrons. And in addition to those electrons, Compton noted that lower energy X-ray photons were being emitted too. So that sentence just summarizes what I was already saying over here on this slide. Now, since the scattered photons had a lower frequency, or a lower energy, I should say, they also have a lower frequency. And that's because energy is equal to HF for a photon, right? So if energy is high, frequency is also high. But at the same time, they have a higher wavelength, and that's because remember that wavelength and frequency are opposites. When one goes down, the other goes up. So going back here for a second, the low energy photon has a low frequency, but a high wavelength, and the high energy photon has a high frequency and a low wavelength. Now, something to be aware of though, is that the photons are both traveling at the same speed before and after the collision. And that's because they're traveling at the speed of light, which we give the symbol c. So sometimes people see here that this photon has a high energy and they think that that means it's moving faster than this other photon with the low energy, and that's not true. They both have the same speed. The scattered electron though, that will not move at the speed of light because only photons move at the speed of light. The scattered electron will have some speed that's lower than the speed of light. All right, here's another picture of what happens in the Compton effect. A couple things I want to point out here. So our incident photon, if we draw a line just extending the line that the incident photon was traveling along, this angle here between the incident photon's path and the scattered photon's path, that's what we call theta. And that's the angle that we actually care about when we start doing Compton effect questions. It's not this angle here that we care about, okay? In fact, you're not going to use this angle that I put an X next to for anything. There's a misconception sometimes when people see this, they think that theta plus the other angle together make 90 degrees. That's not true, so please don't try to use that to solve for anything. Now, when Compton looked at a diagram like this, it made him think of momentum. Do you remember that 2D momentum lab that we did at the beginning of the semester where we had one puck that hit another puck and then both of them went off in two different directions after the collision? That looks exactly like this. It's the same thing. So that got Compton thinking about this. He said that the incident X-ray photon was acting like a particle that collided with another particle, an electron, basically making a 2D collision. And so he thought, in that collision that we just saw, it looks exactly like that collision we studied earlier this semester, where momentum is conserved. So he proposed that the momentum was conserved for the X-ray and for the electron. The other thing that we talked about earlier is that the photon is actually giving some of its energy to the electron. So the photon comes out of the collision with lower energy, and the electron gets that missing energy. And so what we can also say here is that energy is conserved. So we also talked about earlier in the semester how collisions at the atomic level are what we call elastic collisions. The Compton effect is happening at the atomic level. So the collision that we're studying here is elastic. Remember that the word elastic means conservation of kinetic energy. However, we also know that whenever we have an elastic collision, momentum will also be conserved too. So I'll just make a note here. Both things are conserved in the Compton effect. And so how does that work? Well, let's just look at the energy side for right now. This means the energy of the incident photon plus the energy of the electron together equals the energy of the scattered photon plus the energy of the scattered electron. Remember that we use the prime symbol there to show that it's after the collision. Okay, so these two, are the incident ones. And then these two are the scattered ones. And we'll look at the momentum in a minute. So next, calculating the momentum of a photon. So we just talked about how in this collision, momentum is conserved, but earlier in the semester, we learned that momentum is mass times velocity. So how can we calculate the momentum of a photon when photons are just energy? They have no mass. What are we going to do? Well, it turns out we can actually use Einstein's famous equation, which is E equals mc squared, to help us out here. So this is called the mass energy equivalence equation. And basically what it means is that mass and energy are two different forms of the same thing. So we can convert between mass and energy. Or in other words, what I'm trying to say is, say we have a photon with a certain amount of energy. That photon will behave like it has this much mass. So if I rearrange for mass, it's going to be E over c squared. Okay, if I take the photon's energy and I divide it by the speed of light squared, the photon behaves as if it has that mass there. Now, don't use this equation in Physics 30 for anything other than trying to convert between energy and mass. Okay, so just to sum up what I've said so far, okay, Compton's experiment confirmed that photons carry a discrete energy. We learned what the word discrete means in the last lesson, where the energy of the photon is Planck's constant times the frequency. It also confirmed that photons have momentum. That's kind of a new idea that wasn't part of the photoelectric effect. And it confirmed for us that photons are particles, which we did already know from the photoelectric effect. Now, I want to come up with an equation here for the momentum of a photon, just before we keep going. So we know that the momentum of anything is mass times velocity. Okay, but we're going to modify this for photons. So momentum is going to be mass times c, because the velocity of a photon is c. Okay, now this is only for photons. Don't try to use this P equals mc in any other situation. Now, on the last slide, we wrote down that the mass is really E over c squared. So I'm just going to replace mass right here with E over c squared times c. Cancel c. So then we get P is equal to E over c. Now on your formula sheet, it's written this way, E equals PC. So this is the equation that you can use when you're trying to find the momentum of a photon, okay? So E would be the photon energy, and P would be the photon momentum, and C is just the speed of light. Okay, you don't try to use this formula for electrons though, it's not going to work. Okay, so the Compton effect equation looks like this. Okay, so we already talked about what the angle is earlier in this video. Change in wavelength, this refers to the photon wavelength. So delta lambda is the change in the photon wavelength. Please use meters for that. Note that it's a change, okay? H is Planck's constant. When you're using this, make sure that you use the joules seconds version of Planck's constant. M is the mass of an electron, and that's kilograms. C is the speed of light in meters per second, and then that's everything that we need to actually use this formula. Sometimes you might be asked where this formula comes from. You're not expected to actually derive it in Physics 30, but you do need to know that in order to derive it, you would use conservation of energy and conservation of momentum at the same time. But we're not going to look at the details of how to do that. Example 1. Find the momentum of a photon whose wavelength is 1.25 nanometers. Okay, before we do this, I want to show you how to derive one more formula. So we know that E is equal to PC, but then we also know from the formula sheet, E is HC over wavelength. So since both of these things are equal to E, we can put them together and we can write PC equals HC over wavelength. And what we can do is we can cancel out C, leaving us with P equals H over wavelength. So we can actually use this formula here, and it's on your formula sheet, to calculate the momentum of a photon. And so let's go ahead and do that. So momentum equals H, which is Planck's constant. Whenever you're using this formula, make sure that you use the joules seconds version of Planck's constant, and make sure that you convert your wavelengths into standard units. So we're going to write 1.25 times 10 to the negative 9 so that it's in meters and not nanometers. And when we do that, we get 5.304 times 10 to the negative 25. Now it is a momentum, so the units of that could be kilogram meters per second, or remember, momentums could also be measured in Newton seconds. And so after rounding, the momentum of this photon is 5.30 times 10 to the negative 25 kilogram meters per second. Okay, example 2. A 1.24 times 10 to the negative 11 meter X-ray hits metal foil and scatters at an angle of 40 degrees. Calculate the wavelength of the scattered X-ray photon. Okay, so the initial wavelength before the collision happens is 1.24 times 10 to the negative 11 meters. The angle is 40, and we're looking for the wavelength of the scattered photon, which means the wavelength after the collision happens. So we can use our change in wavelength formula. So change in wavelength is H over MC times 1 minus cos of the angle. Okay, so change in wavelength, H, so again, H should be in joules seconds. M is the mass of an electron. So because the X-ray is scattering off an electron, M is the electron's mass, which remember is on the back of your formula sheet. C is the speed of light. And we're multiplying all of that by 1 minus cos of 40 degrees. So pause the video, try to put that in your calculator, and make sure that you're getting this number here. So the change in wavelength should be about 5.67 times 10 to the negative 13 meters. Now, be careful, because the change in wavelength is not actually the answer to the question. We are looking for lambda final. So what we're going to do is write down change in wavelength is going to be the final wavelength minus the initial wavelength. And so rearranging for the final wavelength, we just have to add the initial wavelength to both sides. So delta lambda, so that's 5.67 times 10 to the negative 13. We're adding to that 1.24 times 10 to the negative 11, and that gives 1.30 after rounding. So before rounding, it's 1.296 times 10 to the negative 11, but to 3 sig digs, 1.30 times 10 to the negative 11 meters. Okay, I just want to mention that in some of the questions, you have to actually use conservation of momentum. So I just want to show you how you would set up the formula for that. So we would have the momentum of our X-ray photon and the momentum of our electron. Whoops, and this would be before the collision. So there shouldn't be a prime right here. Okay, so this is before the collision, and that would equal the momentum of the X-ray after the collision plus the momentum of the electron after the collision. So the momentum of the X-ray before the collision would be h over lambda initial. And the momentum of the electron, usually before the collision, that's just 0 because the electron is at rest. And then the momentum of the X-ray after the collision, that would be h over lambda final. And then the momentum of the electron after the collision, that would just be the mass of an electron times the velocity of the electron after the collision. Now remember, when you do this, everything is a vector. So remember, from the momentum unit, things that are left, you have to make them negative. Things that are west, you also have to make negative, for example. And then you can use this to solve some of the questions. And you can also use conservation of energy, which we talked about earlier.